And here we are back again, ELE 210 circuit theory. We have a document here for Lab 7, which also includes some theory. And I wanted to talk about, precision rectifiers. And so we start off, there's a link here where you can look at a circuit we had back in ELE 115 for a full wave rectifier. Now this circuit, it has a sine wave source, in this case 12 volts peak, and just a very low series resistance here of 1 ohm. A 1-to-1 transformer, so if there's 12 volts peak on this side, there's 12 volts peak on this side. And since this is truly an AC waveform, half the time this node right here is positive, with this one being negative, and the other half of the time it's vice versa. This guy is negative with this guy being positive. So in the first case, when this top node is positive, current will flow out through this diode, through the load, back through this diode. So out through D1, back through D4, and back to here. You can think of this transformer secondary as an AC source. When this bottom node is positive, the conventional current will flow out here through D2 and be steered up to the top of the resistor, again going through the resistor in this one direction only, and then coming back through D3 to the other side of the secondary of the transformer, which is our AC source. So we get our full wave rectification in that case. And so in simulating that circuit, we'll get something of between the orange and blue here. The blue is the waveform that we drive both into, and the same waveform we get out of the transformer. And you'll see it goes up to 12 volts. This is 10 volts, this is 15. You can believe that the blue here reaches 12 volts. But the orange just crests over 10 volts and then goes down and hits ground and then comes up. And notice it doesn't just hit it and bounce back up, it stays there for a second. And this difference between the input and output waveforms is caused by the diode drops that we incur, the 0.7 volts. In a full wave rectifier, in each case we traveled through 2 of these diodes, so we incurred about 1.4 volts, 2 times 0.7 volts of diode drop, and that's what we see. Instead of 12 volts, we see about 10.4 volts, or I'm sorry, 10.6 volts here. And so we've lost lost some voltage across 2 diodes. So one wonders, is it possible to rectify voltages that are smaller than 0.7 or 1.4 volts, and or is it possible to just build a rectifier that can perform rectification without losing the cost of the diode drops? Now the diode drops are there because it costs us a little voltage to turn the diode on so that it can conduct in the one direction it conducts in. Well, it turns out we have such circuits. They are oh boy, there's a typo right there. I'm sorry about that. I will update that in the web. So we have such circuits that can perform near perfect rectification. And I think what we'll do is I'll actually go out here, we'll look at a couple of these. Here's an OpAmp precision rectifier, one of our circuits, and we have an OpAmp here, and when the OpAmp is conducting in the forward direction, it will conduct through the diode, but the feedback to the OpAmp is after the diode. So in essence, the OpAmp will compensate for the diode here and put that voltage back in. And let's look at what the waveform looks like when we do that. So I'm going to run the simulation, and you can see I've got input voltage from a sine wave that's 0.1 volts peak to peak. That's certainly a lot less than 0.7. And the output here, we're going to measure that. And because we're building this for the ADALM 1000, we're putting everything on a 2.5 volt virtual ground. When you build this for the ADALM 1000, you actually using channel A, this 2.5 volts is built right into here. So, you know, you won't be connecting the bottom of your source to the 2.5 volts. You'll connect it to ground because you'll have 2.5 volts offset built right into this thing. So let's simulate this thing. And I'm going to zoom in on, say, the last 3 cycles here. And this, other than these little down shots, and you know, you can see here where the blue line, which is the output, blue is V out. Here's V in is a sine wave. V out is flat across here. There's a little bit of funny business going on as we climb up, but the blue waveform is behind the orangey or brown waveform there, and is a half wave rectified signal. Okay, so we you know, there's one of our circuits. If I look at another one of our circuits, we'll look at the ones that we that I put arrows here. These are the 3 circuits I'm going to have you do it for lab 7. So let me see this. So we make this bigger. All right, now this one here, I'm using a piecewise linear, and you can always copy that, but you'll be able to do this in you'll be able to do this something similar to it in the ADALM 1000. Just come up with something similar. You got choices in the input waveform there. And here's a circuit. It's similar to that other one. And here the output voltage is brought back via this feedback resistor, and this is an inverting precision rectifier. See the inverting amplifier here, resistor into inverting input, resistor to the output, and these 2 diodes control the steering so that we only get the positive. Well, in our case, I guess the positive half cycle. So let's. Before I mess it up any further, let's run the simulation and see what we do get here. Alright, so I'll just grab a couple cycles worth of this thing. So yeah, we get an inverting half-wave rectifier. Here's our waveform, which goes as a triangle waveform. It goes 0.1 volts above 2.5 volts and 0.1 volts below 2.5 volts. So it's got a 0.2 volt peak-to-peak swing. But in the section that goes below, and again, there's some hinky-binky business here on these corners. On the blue output waveform, we half-wave rectify this, and we just drive out the half of the waveform. And yeah, we do get some funny business here, but on the other hand, we're down here working at waveforms that are 0.1 volts when the minimum voltage to turn on a silicon diode is 0.7, or probably 0.6, somewhere in there. And even a Schottky diode is in the 0.3 area. So the fact that we're doing this stuff at 0.1 volts is kind of cool. All right, and if this were a sine wave, you'd have a sine wave for the orangey brown, and you'd have these just half wave parts of the sine wave for the for the output waveform. And if you wanted this to flip the other way, well, you could always put it through an inverting amplifier. So that's our, that's the second of our simulations, and let's see what we have here. The last one here is a full wave precision rectifier. It says it's trying to get property of non-object. That doesn't look like a happy time. Let me see if I can find my full wave. Here's a full wave rectifier here. I will fix that link. Right now, and I will update those documents. Let me go into here and let me edit this hyperlink. Well, that time it worked. Okay. So this takes 2 op-amps to do this one, and we'll zoom in. I think maybe we need a little extra room here. So what we have right here you might recognize as our, this is our half-wave rectifier that we just reviewed. And then after it, this is an inverting summing amplifier. So this guy comes in, I got 10K here and 20K here. This guy's going to go in with a gain of -2. This guy, the original waveform, is going to get added to it with a gain of -1, 20K and 20K. And then we're going to get a waveform out of that. Now, let me look at our I have a graphic for that, but let me fix the actual thing here. I'm going to add a rectangle here. We'll put a rectangle right around here. I'm going to call that, where's my, and then I'm going to put another rectangle right around this guy. No. And this guy right here is a precision half-wave rectifier circuit. And then sorry. This guy down here is an inverting summing amp with different input gains. And I will fix this guy. We've saved that. So here's a precision half-wave rectifier circuit, and I believe it's an inverting rectifier. And then here's an inverting summing amp that's going to take that signal times -2 and add it to -1 times the original input signal, and you're going to come back with a full wave signal. And when we do this, if we look at our simulation, and I'll zoom in on just a few cycles here. You can forget the tan signal here, Vx. That's the signal in between the two, but the signal, the input signal is this sine wave, this kind of bronze orangey kind of thing that travels here, and it's a true sine wave. And the output waveform is, it looks like a half wave here, but it's also behind the input waveform. So it's a full wave. It's a full wave rectified sine wave, and again, it's only 0.1 volts peak. So it's getting around the diode drops and giving us the signal that we want. So I'm going to close those out. Go back here. So that's an example of this idea of the precision rectifier. There was a half wave, there was a fancier half wave one, and then the half wave plus an inverting summing amplifier with 2 different input gains. That gave us the full wave rectifier, precision rectifier. So what I want you to do is to build each of these 3 circuits right here on using the AD8542 dual op-amp. And it has 2 op-amps in the package. Again, it has the weird pin out, so you have to kind of figure out where pin 1 really is. And here's a picture of mine, the very first one. You can see it's got the diode. The diode points to to this load resistor out here, and that point is brought back to pin 2 on the diode. The signal comes into pin 3, the non-inverting input. Ground is on 4, plus 5 is on 8. These 3 pins I left blank. It technically isn't the right thing to do. And I return my load resistor to 2.5 volt ground. And my input signal has 2.5 volts of DC offset built into it, so that's why that works. And I got, I got a pretty standard looking half wave, output voltage on the A-Delm. Here's the fancier op-amp, precision regulator. And here you can see during the negative halves of the input sinusoid, I got a positive half sinusoid. So it's a half wave rectifier, but it seems to be an inverting half wave rectifier. And the last one is the full wave rectifier, and you can see I used both sides of the AD 8542. And what you see is I have all my peaks in here, but every other one, the alternating ones, are different heights. And I maintain that's because we're using 5% resistors, where we should be using probably even better than 1% resistors, maybe 0.1% resistors, so that everything comes out equal. But you can see that the circuit is a full wave rectifier, and again, we're working with just 0.2 volts peak to peak here. So precision rectifier circuits, that's what we got. I hope that makes sense, and let me know if you run into trouble on that. And we'll talk to you again about logarithmic amplifiers. All right, take it easy, and we'll talk soon.